Well, hello. It's a little early, so we don't have a full crowd yet, but we're off to a good start. The way we visualize this program, yesterday's wonderful lecture by Michael Mann and today, is that we want to hit, Michael set the stage yesterday in a big way. We know what the problem is. The question is, what can we do about it? And today is meant to be a bunch of talks dealing with how can we respond? What are the ways in which we can mitigate the increase in global gases in the future? There's a wonderful book called Drawdown. I don't know how many of you know this book. Written by Paul Hawken. Not written by him, but organized by him. It's a New York Times bestseller. It's a beautiful book. It actually tells us, and it was put together by a large group of people. It's about 80 or 100 people who contributed to this. A whole set of things that we can do, and an estimate, a realistic estimates of how much this would, each one of these things, if we were able to implement them, could cause a reduction in the carbon dioxide of the atmosphere between now and 2050. These are things that could actually be done. The first one on the list, you'll be surprised to know, is to educate women and girls in developing nations. That doesn't sound like a way to treat global warming, but basically reducing the size of the populations so that we don't have that population pressure in the distant future. Major thing. Regenerative agriculture, which we'll hear about today from Professor Lau. These are things, we're going to talk about those all day today, and I think that you'll find some of these things very interesting. People have to come up with ideas, and you can all be part of it in your own way. And I hope that at the end of the day, we'll have a reception with an open mic. And if you have any ideas and thoughts that you'd like to talk about, any things that you'd like to contribute, come there prepared to say a few words about it, and we'd love to have you talk. Thank you.
And now I'm going to turn over the program to our Master of Ceremonies for the day, Patty Jones. Thank you so much.
Good morning, everybody, and thank you for being here. It's my pleasure to be the MC for this event, in which I will be introducing all of our speakers. Also, just so you know, I will keep us on time, and as you can see from the program, every speaker has a generous hour for a presentation, and some of them might take most of the hour, and some of them are going to end early, and so there'll be probably a good lot of time for questions and answer with the audience. So our first speaker, as you can see here, is Jim Hurrell. He is the Scott Presidential Chair of Environmental Science and Engineering at Colorado State University. He's the former director of the National Center for Atmospheric Research, NCAR, where he was also a senior scientist in the Climate and Global Dynamics Laboratory. His PhD in atmospheric sciences is from Purdue. He's also the former chief scientist of the Community Climate Projects in CGD, which includes the Community Earth System Model, and a former director of the CDG and NCAR Earth Systems Laboratory. His research is centered on empirical and modeling studies and diagnostic analyses to better understand climate variability, and climate change. He's co-authored or authored more than 100 peer-reviewed journal articles and book chapters, as well as dozens of other planning documents, workshop papers, and editorials. He's edited several books and has been acknowledged as a highly cited researcher by Thomson ISI. And of course, he's given many professional invited and keynote talks. So please join me in welcoming to the stage Jim Hurrell.
Thank you very much. Well, good morning, everyone, and thank you for coming so bright and early. I know students don't like 8 a.m. classes, and I know faculty don't like 8 a.m. classes, so appreciate those of you that are here today. It's a real pleasure to be here, and I'd like to just begin by echoing a few of the comments that's already been made. I'd really like to thank the organizing committee for putting together, I think, this very important and very timely symposium on the topic of confronting the challenges of climate change. I'd also, too, like to thank Patty as the main point of contact for all of us coming in. She was just absolutely wonderful to work with and answer questions. And if this talk doesn't hit the mark, I'll blame her, because she said she thought this talk looked great, so we'll see. And I'd also like to congratulate Ted Brown. It's my first opportunity to meet Professor Brown, and I'd like to thank you for all of the work that you have done, the awareness and the attention that you're raising to this particular issue, the books you've written on the topic, and it's a real honor to meet you, and happy birthday. And yesterday I had the opportunity to sing happy birthday as part of the group, and I can assure you I'm not going to do a solo now, so that's a very good thing. And then finally, I'd just like to acknowledge the talk that my colleague and my friend Mike Mann gave yesterday. Fantastic talk. I was sitting in the audience thinking, why did I ever agree to talk about climate change science after Mike? He's a fantastic communicator, but I know he really enjoyed giving the annual interdisciplinary lecture here and did a fantastic job. So let me try to take you through a few of the points that I want to make and explain the rationale for the presentation I did put together. This is a slide, and I'll talk about the source of this slide in just a few moments, but this is a very simple depiction of the observed changes across the globe in surface temperature over the last several decades relative to the first part of the 20th century. And as you can see from this figure, there's a lot of red colors. The red denote a warming in terms of this epoch difference. If you fit something like a linear trend line and average temperatures everywhere across the globe, there's been a warming of about 1 degree Celsius or 1.8 degrees Fahrenheit since about 1900. And this is the very significant global warming that Mike spoke of yesterday. My own research in looking at climate variability and the mechanisms that produce climate variability are interested in things like this. You can see that even though the globe has experienced very significant warming over the last century and really since the pre-industrial times, that warming is not spatially uniform. There are marked regional variations. There are seasonal variations. The two blue circles denote a couple of areas of the globe where the warming has not been very pronounced, although in recent years, warming has been evident in these regions as well. And likewise, you can see other parts of this map where the warming is even greater than what the global average is. And that is because, as Mike described yesterday, there is no scientific debate around the fact that anthropogenic climate change is occurring. But of course, the climate system also varies due to natural processes, El Nino events, other modes of coupled ocean-atmosphere variability. And even though natural variability does not really have a fingerprint, when we average globally and look at global trends over this time period, the natural variability of the system is very important regionally and locally. And of course, there's many stakeholders, there's many decision makers who are trying to understand how to confront the challenges of climate change. And it's a very important component of the problem to understand the role of natural variability in climate predictions and climate projections over the coming decades, and also how anthropogenic climate change influences and maybe modifies some of these so-called natural patterns of climate variability. And Mike touched on that a little bit yesterday when he was talking about the jet stream. So that's what I was originally thinking of talking about, focusing on, is our ability to understand and predict, maybe on decadal or multi-decadal timescales, these natural variations in climate and how that fits in to the bigger picture of anthropogenic climate change. But in looking at the agenda and realizing that Mike was giving this great lecture yesterday, but not knowing how many people attended that, I've decided to try to set the stage a bit myself for the remaining talks today. So I'm going to go over some of the materials that Mike presented yesterday and reinforce some of those ideas. In response to a question, Mike made the point that one of the things we can do is all talk about climate change. And so I spend a lot of my time, a lot of my career has been spent communicating climate change science as well. And as I was discussing with Mike yesterday before his talk, We all tell that story in slightly different ways. So my hope is that perhaps some of the slides that I'll show and some of the points I will make can give you some tools and reinforce some ideas as you talk about this problem, because I think it is very important that we talk with many diverse groups and many diverse stakeholders about, indeed, the challenges and the imperative that we confront climate change moving forward. So to do that, I'm going to give kind of a brief overview. I'll move through this relatively quickly. And I wanted to call out this Climate Science Special Report as part of the 4th National U.S. Climate Assessment that was just released about a year ago. And I'll be referring to many figures from this report. This report is available on the web. It's very readable. There's a very nice executive summary. And if you want to look at some very nice figures and graphs and depictions of what we know about climate change science, this is really a wonderful resource. And it also gives me the opportunity to acknowledge Don Weebles, who is here. If you can raise your hand. Professor, a good friend of mine in the Department of Atmospheric Science here at Illinois. And Don has done a remarkable service in his career in terms of his own personal research contributions, but really playing community leadership roles, such as being the lead author on this U.S. National Climate Assessment. So if you have detailed questions on anything I show, you can ask Don. So yeah, you're welcome, Don. One of the things that I like to try to communicate is I can stand here and I can go through graphs and figures and things that I will. But often, again, going back to this concept of discussing climate change, it's a lot to remember, especially for non-experts on the topic. And another colleague, Tony Leiserowitz at Yale University, came up with his summary of climate change in 10 words. And I really like this slide because when I talk to the public, I really like to try to convey, if you can remember these words, you can really have a meaningful conversation about climate change. The first point is that it's here. This is not something that's going to happen in the future. Mike talked extensively yesterday about the impacts that we are seeing across the globe, especially when it comes to changes in extreme events. So this isn't a future problem. It's here. It's causing problems now. It's us. There's no scientific debate. There's no credible scientific debate. Through the burning of fossil fuels and changes in land use, we are increasing concentrations of greenhouse gases in the atmosphere, and the climate system must respond to that. And we can show that the growth of carbon in the atmosphere is due to human activities. It's serious, okay? The impacts that it's already having, the impacts that are going to grow as we move into the future are very serious. This is a problem we really do need to pay attention to and come up with mitigation as well as adaptation. We have to adapt, but serious debates and discussions about mitigation approaches are required at this point. Again, scientists agree that climate change is real, and I think a very important component of the message, especially when you talk to the public, is don't just give kind of a gloomy, look at all this is happening, this is an enormous problem. There are solutions, and I could not agree more strongly than with Mike than his statement at the end about these are the things we should be debating, having honest policy debates about how to solve this problem. But it is solvable. If 10 words is too many, I have a colleague at CSU that does it in 6 or even 3 if you take the word off. It's simple. That's his word. I kind of prefer straightforward, as Mike said yesterday. It's serious and it's solvable, the main themes. In terms of the scientific consensus, I'd just like to point out that, and the formatting of the slide is a little messed up here, I apologize for that, but you know, it's not just Mike, it's not me, it's not Don, it's not just climate change scientists talking about this. We do have things like the U.S. National Academy of Sciences that was charged with providing independent, objective advice to policymakers. And oh boy, I'm sorry, the formatting, the Mac to Windows transition, I guess. But the key point here is really that our own National Academy highlights that the scientific understanding of climate change is sufficiently clear to justify taking steps to reduce the amount of greenhouse gases in the atmosphere. And you can see that internationally, all of the national science academies agree on the scientific consensus around human-caused climate change and the importance of dealing with the problem, as do professional societies, the American Geophysical Union, AAAS, American Association for the Advancement of Science. All professional science academies or groups have similar statements. And then, of course, there's the IPCC, the Intergovernmental Panel on Climate Change. This was raised yesterday as well. That is a body of scientists from around the world that are convened under the United Nations Environmental Program and the World Meteorological Association to provide policymakers, not be policy prescriptive, but give them a true assessment of our understanding of the problem. And in the fifth assessment report, the conclusion was that climate change is unequivocal. And remember Mike talking about, because of this process, because of this international body, and everyone must agree on the report language, it tends to be conservative. Scientists are conservative by nature. We want to test and retest and make sure that we don't make claims that can't be 100% backed up. But climate change is unequivocal and unprecedented, what we're witnessing now, especially in terms of the rate of change. And that, again, the impacts are very widespread. I also like to emphasize that it's not a new topic. We have been studying aspects of climate change for a couple of centuries now. This is one of the scientists. This is John Tyndall, who is a physicist who spent his career in part understanding infrared properties, physical properties of the atmosphere. And in the 1860s, he was measuring in laboratory experiments what gases absorb thermal radiation, and was documenting that water vapor and carbon dioxide are major absorbers. And then Arrhenius, who was also a physicist, but better known for being a chemist, one of the founders of the modern science of physical chemistry, went on and he won a Nobel Prize actually for chemistry in 1903 and was the director of the Nobel Institute from 1905 on until his death. But a really seminal paper that is often cited in my community is that in 1896 he was very interested in glacial cycles. And he noted in 1896 that carbon dioxide will be building up in the atmosphere due to industry. He calculated the Earth would warm by about 4 degrees for a doubling, which is roughly the number we still have today, in 1896. And also recognized, since he was very interested in the Arctic regions and the onset of glacial cycles, that the warming would be greatest in the Arctic due to the amplification factors in the Arctic. As the sea ice melts, the ocean absorbs more solar radiation. There's a positive feedback effect. Really, really remarkable paper. It's really humbling. As I've gone through my career, I've really appreciated the work of the scientists that have come before us, and too often this work is really not fully appreciated. And then David Keeling, who was a oceanographer at Scripps Institute for Oceanography, and began to measure carbon dioxide directly back in 1958 and really alerted the world to the potential risks associated with rising carbon dioxide levels. That carbon dioxide, an Illinois graduate. I was coming to that, Don, but thanks. Now we're even. So, but this curve is so iconic that it's simply referred to as the Keeling curve. The measurements are taken at Mauna Loa on the Big Island of Hawaii, and I had the opportunity to visit this site just a few months ago. And I also like to point out that the rising levels that are noted by this curve were actually noted in a report in President Johnson's administration talking about the dangers of increasing concentration. So the point is, it's not a new topic. And this is the Keeling curve that Mike showed yesterday. You can see the clear rise since 1958 in global measurements of CO2. Well, point measurements, but it's well mixed globally. And today, we're somewhere in the neighborhood of about 409 or 410 parts per million by volume in terms of CO2. So if you'll bear with me, I don't know if, yeah, this will work. I wanted to show, in trying to make this point, that climate change is not a new topic. We can talk about Fourier and Tyndall and Arrhenius and the like. But this is a little movie clip I really like to show, if you'll bear with me. It comes from a TV series that was aired in the United States in the 1950s, GE Science Hour. And the producer of this film was Frank Capra. I think we all know of Frank Capra. Won 3 Oscars for Best Director and nominated for 2 others, including It's a Wonderful Life. He was a pretty conservative fellow. He strongly opposed FDR, a big proponent for American individualism, but he was also a scientist, had scientific training, and he really valued that role. This particular clip is taken from an episode of the Science Hour where they talk about the weather and what the weather's all about. But they also talk about climate change and the risks that it poses. So I'm going to start this, and hopefully the volume works. I'm trusting that. But 1958 on American television. No volume. Can we get volume?
What would happen if we could change the course of the Gulf Stream or the other great ocean currents, or warm up Hudson Bay with atomic furnaces?
Extremely dangerous questions, because with our present knowledge, we have no idea what would happen. Even now, man may be unwittingly changing the world's climate through the waste products of his civilization. Due to our release through factories and automobiles every year of more than 6 billion tons of carbon dioxide, which helps air absorb heat from the sun, our atmosphere seems to be getting warmer.
This is bad?
Well, it's been calculated a few degrees rise in the Earth's temperature would melt the polar ice caps. And if this happens, an inland sea would fill a good portion of the Mississippi Valley. Tourists in glass-bottom boats would be viewing the drowned towers of Miami through 150 feet of tropical water. For in weather, we're not only dealing with forces of a far greater variety than even the atomic physicist encounters, but with life itself.
So again, 1958, and I really like to emphasize this. Mike talked a little bit about some of the political nature of the climate change science debate. One of the things that we often have to respond to is this is something that we've sort of created so that Donna and I can get more funding for our research. And I really like to show these kind of clips to the public. So some basics. I know this is a diverse audience, but I know that you know the basics, so I'm not going to spend time on this. The greenhouse effect. You know, what powers life on Earth, what powers the weather and the climate systems is solar energy that passes through the atmosphere. Much of it is absorbed at the surface of the Earth. The Earth re-radiates that as infrared radiation, and then it's the greenhouse gases in the atmosphere that capture that infrared radiation and re-emit it in all directions, including back down toward the surface. And of course, the greenhouse effect is a good thing. It allows us to live on this incredible planet. It's just the right natural balance, the greenhouse effect on the planet Earth. We can think about Mars, which has an atmosphere made of CO2, but very little methane, very little water vapor, not enough to really reinforce the greenhouse effect. So the planet of the surface of Mars is largely frozen. In contrast, Venus, which also has an atmosphere with CO2 levels about 300 times that found on the planet Earth, has produced a runaway greenhouse effect so that the surface of Venus is warm enough to melt lead. So the greenhouse effect is just right. Water vapor is the key absorber, but the buildup of CO2 means that we're changing the system. And that's the problem. We're increasing greenhouse gases very rapidly. We know this is due to human activities. The rate of change greatly exceeds anything that we've seen in nature. And that simply means that more heat is being trapped in the system. This gets back to the understanding, and the argument is fairly simple, very straightforward. It's not a question about whether or not we'll see consequences of this. The questions, the scientific questions, are precisely how, where, at what rate the Earth will be responding to this increase in greenhouse gases. This is another figure that I really like to show. It puts it in historical context. Paleoclimatology. We can analyze the air bubbles that are trapped in ice cores. And again, remembering CO2 is a very well-mixed gas globally. And this shows, if you will, the natural variability of the system. These minima, around 180 parts per million by volume, represent atmospheric CO2 concentrations during the ice ages, when ice a meter thick built up over many of the continental areas. And the peak here in these interglacial warm periods is around 280 parts per million by volume. What I like to point out is that due to these natural variations, which relate to variations in Sun-Earth orbital geometry, it takes some time to move from these cycles, from about 180 up to 280 parts per million by volume, about 15,000 years or so, roughly speaking. And these are sort of the natural levels of CO2, at least over the relatively recent past of Earth's history. Where are we today? Again, we're at about 400. This rate of increase, we've made this increase over a very, very short period of time relative to the geologic record. And this is where we're headed. This is where we're headed if we continue to emit greenhouse gases at the rate that we're currently emitting them. To me, this is a very scary graph. This really puts into perspective how far outside the range of natural variability we are, how we are conducting an experiment with this planet that has never been conducted before. Greenhouse gas concentration CO2 have been very high in the atmosphere before on very long time scales, tens of millions of years, but it was a very different planet. This is the anthropogenic perturbation on these natural cycles. So what are some of the symptoms? I'll go through this very quickly. As I said, it's not a question about whether or not the planet will respond. It's exactly the nature of that response. More heat is being trapped in the system. So one of the effects of that is the warming of surface temperatures around the globe. This is very similar to that first plot that I showed. This is just looking at the change in temperature since 1950, when we have more global observations. And you can see that the warming of the planet is evident nearly everywhere over this period. We can average all of these temperatures together across the globe and produce these kind of plots that you've often seen before. This is just the evolution of annual global surface temperatures since 1880. These are anomalies, so relative to the average from 1901 to 1960. If you just remove that average from the individual annual means, the blue bars indicate where global temperatures were cooler than this average, the red where it's warmer, and you can see a very clear upward trend. If you look at the details of this plot, like I've said, about 1 degree of warming since 1901, you can really see how rapid the increase in global surface temperatures has been over the last several decades, since about 1979 or so. 2016 is the warmest year on record. You can see the second, third, and fourth warmest years there. It turns out that 17 of 18 years in the warmest record have occurred since 2000. The exception being 1998, when there was a very large and significant El Nino event, the natural variability that also contributed to the warming of the planet in 1998. The coldest year in the 21st century is 2008, and 2008 is the coldest year in this century, but it's warmer than all years prior to the 20th century in this record of global surface temperatures. You can average the data even further and look at decadal averages, and when you do this in terms of surface temperature, you can see very clearly this indication of a warming planet. We can look at the US. This is the plot of temperature change over the US. Again, it's about a Celsius of warming since about 1900 when averaged over the United States. But now when you start to look on regional scales, you can see more heterogeneity, more details in this pattern, including a relatively lack of warming over the southeast United States, and there's a lot of studies trying to understand that. But even in recent years, this region of the U.S., about 95% of the land area of the U.S. has experienced warming over the last century. And we often talk about temperature wherever we put thermometers. If we put thermometers in the oceans, on the surface, if we take measurements from balloons or from satellites looking down from space, we see that the planet is warming. We see many other independent measures that are physically consistent with the indications of a warming world. And many of those are listed here on this slide that we could talk about. And when we think about the future, the extended outlook, business as usual, if we keep going about things the way we are, it's going to become much warmer, and the impacts are going to become much more pronounced. This is a plot that Mike showed yesterday. I think it's very important we can think about changes. And when you talk to the public and you talk about 1.5 degrees of warming, it doesn't sound like much. But where that impact really comes in is when you shift this Gaussian distribution, this bell curve to the right, you can see the very significant changes that occur in the so-called extreme events. So if you just think about this as temperature and you assume there's no change in the shape of the bell curve, no change in the variability, just a shift in the mean, even if that was all that was happening in a new climate, what we used to think of as very cold weather or cold extremes occur much less frequently, and the very cold extreme temperatures we witness will no longer occur. Conversely, what we used to think of as record heat now occurs much more commonly, and we set new records in terms of extreme temperatures, which then has implications for drought and heat waves and wildfires and impacts on human health and the like. And we can see this when we look at the data. So this is a plot looking at surface temperatures over the northern hemisphere. Again, averaged over this period from 1951 through 1980. You can see this very nice sort of Gaussian distribution. You have an average. You have the climate system is variable and weather is variable, and we have cold spells and we have warm spells. But if you begin to just march through the decades, this is 1981 through 1991, this distribution is indicated by the green line. You can see in the data this shift in the extremes, which is a very nice, simple plot to show this is what we are witnessing. Mike referred yesterday to the European heat wave, and there's many, many, many other examples we can give of changes in extremes. This is a plot that I often show. One of the nice things about looking at anomalies over Europe is there's very long instrumental records that actually go back to before 1800, but this is looking at 1850 up through several years ago. This is the heat wave in 2003. And as a climate scientist, Don and I will get a phone call, and what the media often wants to know, whether it's this heat wave, whether it's Hurricane Michael, any number of events, is the question is, Jim, is this because of global warming, or is it due to the natural variability of the system? What's going on? And I think the important point to communicate is those really aren't the right questions. Climate change is occurring, okay? Natural variability is occurring with this background of climate change. So it's a combination of the two. And this slide illustrates that. The very rich natural variability of the climate system causes these changes from one summer to the next in this particular measure. Some summers are cooler than average, some summers are warmer than average. That's the natural variability of the system. Roughly speaking, that same magnitude of variability is still continuing, but now it's imposed upon this upward trend, which means it's much more likely that we're going to see record-setting events such as this heat wave. As was also described yesterday, and I think it's an important point to communicate, when we think about this, there may be things that are confusing for the public at first look. Wait a minute, climate scientists are saying the planet is warming, so I kind of get it, that it's going to be hotter, we're going to have more heat waves, we're going to have maybe more droughts, more wildfires, but how can it be producing all of this flooding as well? And again, it's relatively simple. Over the oceans, more water evaporates into the atmosphere. As Mike showed yesterday, a warmer atmosphere holds more moisture. So when it rains, even if the dynamics of the system don't change at all, when it rains, on average, it's going to rain more. It's going to rain harder. That's going to lead to more flooding events. Likewise, over dry regions or semi-arid regions, the little bit of moisture that's in the ground is going to be evaporated out. The rest of the energy just goes in warming the surface, and this leads to more pronounced heat waves and droughts. I'm going to show one other movie. This is produced at the institution, as Patty said, I was part of for the first 28 years of my career in the National Center for Atmospheric Research. This is a very kind of lighthearted but nice cartoon that illustrates what we're seeing and why we're seeing it. And it has to do with baseball, so I don't know if there's baseball fans out here. Cardinals and Cubs fans, I know. I'm a long-suffering Reds fan, so my season's been over. But here we go.
What do steroids in baseball have in common with climate change?
Well, imagine a baseball player who's been taking steroids. This baseball player steps to the plate and hits a home run. And you ask the question, was that home run due to the steroids? If you look at the number of home runs he hits over a season when he's taking steroids and compare that to a previous season when he wasn't taking steroids, it is only then that you can figure out that the steroids have made him more able to hit a home run because it's made him stronger, and the chances of him hitting a home run are greater. So by adding just a little bit more to those naturally occurring steroids in the human body, we change the background base state of our systems.
Okay, got it. But a lot of bad things happen when you take steroids, right?
The greenhouse gases that we're adding to the atmosphere from the burning of fossil fuels are the steroids of the climate system. The atmosphere has very small amounts of greenhouse gases that occur naturally. So by adding just a little bit more of those greenhouse gases by the burning of fossil fuels to the air, we change the background state of the climate system. We increase the temperatures just a little bit, but that increase of temperatures is enough to shift the odds toward a much greater chance for extreme heat events and extreme precipitation events.
Normally, you'd expect record lows and record highs to balance out over time. But now we're getting almost 3 record highs for every record low.
So just as a baseball player on steroids can occasionally strike out,
you're out.
Climate system with increased greenhouse gases can still experience record cold temperatures, but the chances of record high temperatures are still much greater.
And that's what steroids in baseball have to do with climate change. To find out more about climate change and extreme weather, check out ucar.edu/atmosnews.
Okay, so I think that those, again, I know this is a very accomplished audience, but there's a wide background of people, and again, this is all in the spirit of the importance of communicating this, communicating it to our colleagues, communicating to the public, and for me, these kind of tools really help. I'm not going to go into detail on this. This is really speaking to the fact, and I've mentioned several of these already. There's a lot of impacts. These impacts are going to be growing worse and more pronounced as we move into the future. Adaptation mitigation strategies, I'm really looking forward to some of the talks that follow today, beginning to indeed discuss how we confront this challenge. That's not my particular area of expertise, but it's critically important. We have to adapt. We are committed to a certain level of climate change. You can think of it such as the oceans. The oceans are warming as a result. Those oceans aren't going to cool down. Even if we reduce emissions down to 0 emissions, that warming is going to continue on the timescale of centuries. So climate change is occurring, it's going to continue to occur, we're going to have to adapt to that. But we can really have this debate and this discussion around mitigation options and the best way forward for our planet. At the risk of overplaying my card of showing movies, I'm going to show one last movie. Then I'm going to begin what I wanted to talk about originally, but that's going to be just a few minutes. Toilets in the Smart Grid. This is a film that was done by a professor at Penn State, another colleague of Mike Mann's. His name is Richard Alley. And it's really trying to illustrate that there are strategies to solve this problem. And we've been confronted with other challenges in the past that seem insurmountable, but we've been able to handle those challenges. So let me just show this one last movie, and then I'll start to wrap things up.
So, the Earth provides lots of choices for clean, low-carbon energy. It shows that we can do big things to get benefits that none of us would ever walk away from.
Okay. So I think that's just a beautiful narrative in a short film that really conveys, when you talk about climate change, that we can come up with solutions to this problem. I think that's very, very important to convey in any talks on this topic. So I appreciate you putting up again with a bit of a background. I hope that helps set the context for the day. Now my daughter, who's here in the audience, Rachel Hurrell. Rachel, raise your hand. There you go. She was giving me a hard time that she's heard me give that talk several times. So I had to put a few news slides in for Rachel, and if you can bear with me. This is just touching very briefly, because I got 10 minutes or so, very briefly on some of my own work. And I do want to convey, it goes back to this point that anthropogenic climate change is occurring. It's a very serious problem. We have to figure out how to deal with this problem. But when you talk with decision makers, with various stakeholders, with water managers, with people in the agricultural sciences and whatnot, you know, the climate system is extremely complex. And climate variability due to natural factors is continuing to occur. Anthropogenic climate change doesn't mean that becomes the only game in town. So if we're seeing trends in certain areas, what's the likelihood that these trends might reverse? Even though the planet in general is warming and, say, drying in my part of the world, in Colorado, what does it mean if we have multiple summers or even a decade or two of wetter than average conditions? Now, in the public discourse, often that's twisted into, see, I told you there's nothing about this climate change thing. But scientifically, it's a very rich problem, and I think it's very important as I talk with those kind of stakeholders to explain what we're witnessing in the climate system and why. So my own interest is very much what are the mechanisms of natural variability and what is the predictability of the system on those longer time scales. We often talk about the inherent limit of predictability for the atmosphere is maybe only out to about 10 days or so. Weather forecasts are really very skillful out to that time, but what can we really say? What can we tell society about what to expect over the next decade or maybe 2 decades? And we know the climate system is very rich with variability on these time scales. Can we actually predict that? And that's what I'm very interested in terms of my own personal research. And this is just, you know, kind of going back to this figure when you think about this pattern of temperature change, relatively cool, for instance, over the Northwest Atlantic, warm over the Northern Hemisphere land masses. This is very clearly tied to changes that we've seen in the circulation of the atmosphere over this time period. This is a plot that shows the difference in sea level pressure. Again, a very simple difference plot like the one we showed for temperature. Just looking at how the pressure patterns have looked over the last several decades compared to the decades before that in the middle part of the 20th century. The blue colors indicate where there's low pressure, so you can think about a low pressure system and counterclockwise flow. The red, high pressure. And so the flow around this being this direction, around the low pressure this way. And if you just look at the North Atlantic, this flow, this change in the circulation has produced more colder Arctic air coming down over this part of the world. That relates to that cold spot. and more strong west to east flow of relatively warm maritime air during the winter season over Europe and downstream into Asia. And that explains dynamically much of the warming that we've seen over that part of the globe. These are the kind of things that are very important. As you can see, it's really occurring on very long time scales. This is just a plot of sea level pressure over the North Pacific, and the difference, the gradient in pressure here. And I just put these, they're not really scientifically robust, just sort of eye indications with your eye of these different epochs or different periods of time. And you can see that these variations are very significant, very robust. They occur on decadal and multi-decadal time scales. So one of the aspects of climate science that we're focusing on quite a bit is to what extent can we predict these and understand these changes and give society useful information on, are we going to stay in this regime for another 10 years? Are we going to shift to that? Because again, it really dominates regional climate variability on fairly large spatial scales, all in the background, all in the context of an overall changing climate. This is just a slide I like to show that kind of illustrates how this problem has been somewhat ignored. This is a slightly old article about a decade ago by Ed Hawkins and Rowan Sutton, published in 2009. It's looking at some of the model simulations for the fourth assessment report of IPCC back in that point in time. There's different emission scenarios here, the historical surface air temperature record, the observed record. And what you can see is that there's various sources of uncertainty when we talk about climate model projections into the future. One of those is called forcing or scenario uncertainty. What pathway are we going to take? What are we going to do about emissions of greenhouse gases as we move into the future? We can take different approaches, and we can either make substantial decreases in emissions or remain on more business as usual path. And that produces a range of climate outcomes given by these solid colored lines. Climate models are also not perfect, so if you run a set of different climate models with slightly different representations of the system, because the system is very complex, and how the physics of the system are represented vary from one model to the next. Even under the exact same forcing scenario, you get a range of responses. So if you just look at, for instance, this blue curve, you see that there's a spread of outcomes. And this spread is very important to understand and communicate. But all these little spaghetti lines, which you can't see the individual lines very well here, represent then this natural variability, not just averaging across all the models under all these different scenarios. That's what we do in the field of climate science to isolate, to depict what the forced climate change signal is, which is critically important. But we intentionally average out all the natural variability of this system, which indeed is large and important. So this is really the problem, is that we have anthropogenic climate change occurring, but we have these very large decadal and multi-decadal variations that can really dictate climate over large portions of the globe. And so to what extent is that predictable? So we use models. This is the model that's been used for this particular study. It's called the Community Earth System Model. Patty referred to the fact that I was in charge of climate projects at NCAR. One of those projects, I served as the chief scientist for the development of this model. It's a very complex model. For a long time, climate models really represented what we call the physical climate system, representations of the atmosphere, the ocean, the sea ice, and the land surface in various degrees of complexity. Now we're understanding that it's not just the lower atmosphere that's important for climate, but indeed the whole atmosphere extending to outer space. The chemistry in the system is incredibly important, and we'll hear talks related to that. Ecosystems and how they're being impacted and how they feed back and influence is very important. And not only sea ice, but land ice. Mike referred to his talk yesterday that several decades ago we viewed the Greenland ice sheet, the Antarctic ice sheet, as something that was going to change on very, very long time scales. Basically, these massive blocks of ice were going to stay there, even in the context of climate change. But now we're seeing that they're melting, that the dynamics of those systems are changing more rapidly. So it's important even for studies of the next century or so that we begin to include representations of the ice sheets. So this is just a little bit about this model. This is a study that was published by some colleagues of mine in the Bulletin of the American Meteorological Society, and they describe a very rich set of runs, and perhaps it might relate to some of your individual research interests, and we can talk more about these set of runs. But the experimental design is basically this. You run the model under some pre-industrial control. You then begin what we call a 20th century simulation, where we have the best estimates of changes in radiative forcing over the 20th century. But in 1920, an arbitrary year, but just to illustrate the impacts of unpredictable natural variability, what we did was we perturbed just the atmospheric initial state by this very small temperature perturbation at the very lowest levels of the troposphere, of the atmosphere above the surface. Just barely perturbed it. And this is this chaotic effect, okay, the butterfly effect that Ed Lorenz documented, that just a slight perturbation causes the atmosphere and indeed the climate system to go on different trajectories. And this relates to the natural variability of the system. And what it means is that if we look at projections and we don't average across these just to isolate the greenhouse gas force signal, it gives us a spread that's inherently unpredictable when we look beyond timescales of maybe 10 or 20 years, if we look at, say, the next 50 years. This is what it looks like. So we have a control, we have an individual member, we then perturb it, and the gray lines illustrate this spread. Now this spread doesn't look very impressive, and that goes back to the statement that I made earlier. Okay, the natural variability is not going to have a very strong fingerprint when you look at global averages or hemispheric averages or annual averages, okay? But it certainly does when you look regionally. So if we look at climate trends over the next 50 years, not just the next 10 years, but what about the next 50 years? What does this imply? There's a lot of plots here. I've plotted 40 of the 42 ensemble members. This is just looking at the change in temperature over the US over the next 50 years, okay? Under the same forcing scenario, over the same greenhouse gas forcing scenario. And you can see a lot of commonalities. When we average across all of this, you can very clearly see that the model projects an average warming over the US. It's very pronounced, several degrees centigrade, especially over the northern regions of North America. But if you really begin to look in detail at each one of these individual maps that I would argue are equally plausible outcomes to the extent that the model is representing well the actual system, and we have many reasons to believe it does a very good job in many aspects of representing the climate system, you can see that there's really a wide spread of outcomes where, for instance, portions of the northwest United States and western Canada show very pronounced warming, but other simulations show much less warming or cooling. This is critical information to convey to stakeholders and users of this kind of information. We can understand that by when we look at an individual model simulation, which is a credible simulation of what might happen over the next 50 years. We can contrast two runs, just to say run A and run B. The colors depict the temperature change over North America. The contours represent the change in sea level pressure, a measure of the atmospheric circulation. And you can see two very different depictions. One model simulation shows that high pressure is going to increase over the North Pacific, which produces this direction of a flow. Again, takes relatively cool air from the Arctic down into this portion of Canada and the western US. In contrast, low pressure evects relatively warm maritime air over this region and really amplifies the warming that we'll see as a response of anthropogenic climate change. If you average across all 42 model simulations to look at what the response of the model is to greenhouse gas forcing, that's the forced response that's common to all of the runs. And if you simply subtract the forced response from the total, that gives you the temperature fingerprint of the internal variability of the system. And I think you can see very clearly that fingerprint can be very, very significant. And so this is something that I think is equally important to communicate as well. So that's my talk. I won't take the time to run through the conclusions. You can read it for yourself. And again, I hope this kind of hit the mark, because it was kind of hard for me to decide exactly what I should focus on in this talk. So thank you very much. It's a real honor to be here, and I appreciate it. And I know I've used up my time, but maybe one question? Or?
Right, yes. Why don't we have our next speaker come on up and
Okay.
get her computer set? And so while we're doing that, let's take advantage to have a couple of questions for Jim.
Ted and then Don.
Those models that you just talked about, do they have a kind of directionality to it? That is, I know that there are various directions that this thing might move, but once it starts in a certain direction, is there a sort of momentum there so that if you sense that one of those particular trajectories is in progress, you can use that to project what might happen in the future?
Yeah, and in a paper that we wrote, myself with several of the co-authors I listed, we talked about that specific problem. It all relates a little bit to maybe even some of these like tipping point arguments and whatnot when certain thresholds are crossed. That gives you a better prediction of how the predicted response is going to evolve. But still, you know, I think that the key point is the amount of natural variability in the system can really cause very different trajectories. Again, this is on, you know, regional spatial scales. But what I was hoping to illustrate with those plots is the regional scales aren't very small. I mean, they're, you know, they're continental wide scales, and so that's very important. Don?
My question was kind of related. In some of the runs that you did, some parts of the U.S. showed a cooling effect, and could you comment on what kind of led to those portions of the U.S. that seemed to get some cooling?
Yeah, it's almost, in our analysis, it's really strongly dominated entirely by the dynamical response of the system in those simulations. So it's the changes in sea level pressure, the changes in atmospheric winds, the positioning of the jet streams, which is entirely dynamical. You can actually then regress out that dynamical component and be left with another indication of just the force response. And I think that's very important when we talk about comparing models with observations. You know, how well does a model capture? Geez, we're not seeing the warming that we've witnessed in the real world. It could be that dynamical response. And so factoring that dynamical component out, I think, gives you a truer evaluation of how the models perform against observations and model-to-model comparisons as well.
All right, I think we're going to cut you off there because we're
Okay.
speaker. Thank you so much.
Be happy to talk with you at the break.
All right, Joe will be
Okay.
around for the break. Thank you very much.
Thank you.